get started. Next talk here is by Allan Campopiano, and it might look normal, but this distribution will ruin your stats. So let's give a nice welcome to Allan.
Hi, everyone. Thanks for being here. Right, it might look normal, but this distribution will ruin your stats. So you are at a stats talk, but don't worry, this is really intended for a general audience. I'll do my best to avoid the stats jargon that can come along with this material. A little bit about me before we get started. I'm a data scientist at DeepNote. We build a fully collaborative data science notebook, and I'll be analyzing some data in DeepNote a little bit later on. I have a background in cognitive neuroscience. That's where I learned to code and sort of fell in love with all things data. And in my spare time, I like to develop stats software, mostly to try to make newer stats methods a little bit more accessible to newcomers. All right, obligatory why are we here slide. So look, we use statistics all the time to make decisions based on our data, right? It's a very useful tool. And you know, if you look closely, we see stats everywhere in pretty much every domain you can think of, right? Business, social sciences, natural sciences, engineering, healthcare, you name it, stats are everywhere. So it pays to know how to use them properly. And in general, this presentation is really a look at some of the pitfalls of traditional statistics and some of the newer tools that I'm going to introduce in Python that can help you overcome those challenges. I want to give a respectful warning because in about 20 minutes, I'm going to analyze some data from a social science study on sexual attitudes. So I wanted to give a fair warning about that. There's certainly no imagery, no discussion of non-consensual behavior, and no discussion of assault or anything like that. It's at a very high level, but I wanted to give you a warning, and I'll warn again before I get into that analysis. All right. So let's take a look at our roadmap for this presentation. In part one, we're going to look at the distributions we actually find in nature. And you may already have some idea of that, right? You may already have some intuition about that. If you were to go out into the world and collect many, many samples and plot them, what shape do you think they would take? We're going to talk about that because people have studied this empirically. In part two, we're going to look at why being close to normally distributed is not really enough. And what I mean by that is, how do small departures from normality affect our statistics, affect our ability to interpret our data? And the Python part comes last. In part three, I'll introduce a new Python library for robust statistics, as well as some resources for learning how to reason about modern methods and some of the challenges with traditional methods. Okay, sound good? All right. So part one, the distributions we find in nature. I'll start with a question. Just raise your hand if you think the yellow curve here is normally distributed. Any hands for yellow? Quite a bit. Yellow is popular today. All right. And how about blue? Wow, that's actually more. That's amazing. I've given similar talks, so I'm keeping track of all of this data. This is fascinating. So the yellow curve is actually normally distributed. So everyone who said yellow gets a prize at the end of this talk. No, I'm just kidding. The blue curve is something that's referred to as a contaminated normal distribution. And contamination is really just a way of saying there's a higher proportion of outliers in the blue curve here, the blue population, let's call it. And you can tell this, if you look closely, you can tell that the tails, the edges of the distribution are slightly higher on the y-axis for the blue curve. I don't know if you can see that. But that's, we would say the blue curve has heavier tails relative to the yellow curve. And so that's an indication of a higher proportion of outliers. Okay, so that's what we call contamination. It's quite fascinating though, isn't it? It looks normal, it's bell-shaped, it's symmetrical, right? But it definitely does not behave like a normal curve, and we're going to get into some examples of that. All right. So it turns out that contamination, as well as other characteristics like skew and multiple modes, those are actually the characteristics that we tend to find in nature when we collect very, very large data sets. And I think this runs counter to common thinking that the normal curve is built into nature. It's God's curve, so to speak. And there's been several papers on this, and it's very interesting. This is like the classic one by Theodore Michieri, The Unicorn, the Normal Curve, and Other Improbable Creatures. It's an amazing title. But definitely check this paper out. It's super fascinating. And at the end of the paper, Theodore says, look, normality in nature doesn't exist. And all of the normality assuming statistics should be questioned. And maybe we should look for some other robust methods, you know. So that's partly what we're going to talk about today. Just as an aside, because I think it's really interesting, I don't know if you know this, but the normal curve has an absolutely fascinating history and oftentimes very controversial history. I put together some quotes here and how they sort of depict the attitudes towards normal curve over time, and I just wanted to share it with you because it's really interesting to me. I'll read these, so it's okay if you can't read that. But in 1888, Galton said that if the Greeks had known about the normal curve, they would have made it a god. And it brings order to chaos. And if you know anything about the central limit theorem, you could kind of understand why people would say this. But love for the normal curve weakens a little bit, and towards the end of the 19th century, Pearson says, this is a great mathematical convenience, but I don't see any reason why we should assume the normal curve. I'm paraphrasing. And then love is kind of like at its all-time lowest for the normal curve when Gossett, under the pseudonym Student, came out with a t-test to deal with small sample sizes and small departures from normality. And I think at that time, there was a lot of excitement about methods that could overcome this assumption that everybody kind of felt like was maybe not the right assumption to make. But you know what? The normal curve has this strange grip on us. And love for it started to come back. Fisher showed that when universal normality could be assumed, inferences of the widest practical usefulness could be drawn from samples of any size. Fascinating statement. So we were kind of getting away from the normal curve, but it pulled us back in. And then towards the 80s, and I would suspect even to this day, we see sentiments like this. Measurements of many variables are good approximations of the normal distribution. God loves the normal curve. And here we are, back at this idea. God's back into the picture. It's like the normal curve is built into nature somehow. And I do suspect that if you were to open any introductory statistics book, you would find this kind of sentiment, maybe implicitly, but that the normal curve is built into nature. All right. I've been giving the normal curve a really bad rap here, but I haven't yet shown you what happens if you assume normality, and how big of a problem is that? So let me show you one of many striking examples I could show you. All right, so let's just focus our attention on the yellow distributions, the yellow populations, let's call them, on the left. Now, you can see those are definitely two different populations. They're split by about 0.8, so it's a sizable effect. Now, if I were to reach into the yellow curve on the right, so take a sample, and take a sample from the yellow curve on the left and conduct a t-test to test if there's a statistical difference between those samples, I could do that, I could use Python and use a computer and do this simulation many, 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 many times, right? And then I could simply ask myself, what's the proportion of significant results? Right? Easy to do. And it turns out that about 90% of the time, I will find a difference, a statistical difference. Now, I know I'm leaving out some details here, but if you want to know more about the parameters that go into a simulation like this, well, I'll be sharing all of those resources. But this basically means, hey, 90% of the time I find a difference, and it's good because it's a reflection of an actual true difference in the populations. In real life, you never know what your population shapes are, but when you use simulations, it can really help you understand interesting patterns of effects. So, what happens when we do the same thing, but we do it with the contaminated normal distributions, these two populations that are also separated by the same effect? It turns out that we can only find an effect about 20% of the time. That means 80% of the time we're basically saying, we don't have any evidence here for an effect, right? And that would be a false negative. So this is really a reflection of something called power, right? Which is the probability of finding an effect if there is an effect, and there definitely is an effect here. So this is one of many striking examples I can show you, and I'll show you all the code for this a little bit later. All right, this is a Python conference after all, so we should probably talk about Python. One of the criticisms of modern tools for dealing with robust statistics is that the software is just not any good, and it's not that accessible, which might contribute to why we still see traditional statistics being used quite frequently. So I tried to help with this problem, and I wrote this paper and this library called Hypothesize, which to my knowledge is the only Python library dedicated solely to robust statistics. It's a new library. I had the great honor of publishing this paper and the software with the eminent statistician and expert in the field of robust statistics, Rand R. Wilcox. And I'm going to tell you a little bit more about him later. But it's really cool. Rand has curated like hundreds and hundreds of unbelievably cool, robust functions. And they're all just sitting in a text file, and they're all written in R. So I did nothing other than take the ones that I wanted out and write them in Python, put a nice API around it, write some docs, and then make it part of the Python library ecosystem. And now we have robust statistics for Python. All right. Just another note about this for the stats folks out there. If you like t-tests and ANOVAs and regressions and correlations, all of those methods have an analog that basically works very similar in Hypothesize. So it's not like you're going to be dealing with like super weird methods that you won't recognize. All right? Okay. Demo. So I'll give you a demo. You know how live demos go. Also, I wanted to give a respectful warning as well, because we will be talking about that study on sexual attitudes. Okay, and again, this is spoken at a very high level, so there's certainly nothing graphic. All right. Okay, I'm going to get out of my Google Slides. Wish me luck. Say some prayers. You know how these things go. All right. Just bear with me for a second. This is my repo for Hypothesize. Okay, so come and find it. It's really starving for stars right now. So, if you have a second. All right. As I hinted at earlier, like part of the motivation for writing this kind of software is to make it easier for people to onboard to new methods, And one example of how I can do that is, so if you look at this little code snippet here, this is just simply the code snippet to run a robust correlation. So instead of Pearson's R, you can run a Winterized correlation instead. But what's cool is that all of the hypothesis tests in this library are associated with their own live running Python notebook. So this way you don't have to worry about like writing all the boilerplate code and from scratch and everything. You can just click a link and then boom, you're in a notebook and you're ready to go. So for example, if I click this Launch in Deep Note button, it'll launch this Winterized Correlation. And it'll like fire up a machine and you'll be able to like basically just run the notebook from start to finish. It'll even create sample data for you in the structure that the function expects. And it kind of is there to teach you, what the inputs look like, based on fake data. Then you can just drag your own data in there and use it if you like. Now, I already have one. I'm just going to close this because I already have one here. And if I run the notebook, it'll pip install Hypothesize. Okay, nothing too crazy about that. Here, let me just zoom in a bit more. All right. I can import the function that I need for sample data and import the actual correlation function itself. I can create some fake data, no big deal. I can pass each of those columns into the function and print out my results. And now I get a dictionary, and this dictionary gives me a p-value, it gives me the n, it gives me the covariance, it gives me the correlation. Okay. Now, this is just fake data, so it's not that exciting, right? But remember I told you about that cool study? Let's talk about that now, because it represents a very interesting challenge for us. So this is a study on sexual attitudes collected by the author Miller. And basically what this study is all about was they asked thousands of people, how many sexual partners do you want in the next 30 years? Now, if you think about that for a second, you can only imagine the number of outliers in this data set. And it's very difficult to know how to even deal with it. So let me show you a little bit how the data look, and then we can run some stats. But what's interesting is that we'll run a traditional t-test to compare groups, and then we'll run a robust t-test, like a percentile bootstrap test. No, it's actually called a bootstrap t-test. Anyway, there's lots of flavors of bootstrapping. Okay, so we'll do this and we'll see how all the results shake out. So I'm just gonna run these blocks, import everything. I got a function for cleaning some data. I'm gonna clean it, then I can print the data out, and let's see if I can get in here close enough so I can give you some sense of what's going on. Okay, so the max value for the male group is 2 million. The max value for the female group is 3,000. If I filter this column by just any value, let's just say I throw a 1 in here, and we can look at some of the other values. There's actually lots of 1s in this data set. There's lots of 0s as well. There's a 12, there's a 10, there's a 1572. I don't understand it, but it's a really interesting data set. So let's get to the good stuff. I'll pass all of this data into a traditional t-test, okay, and we'll take a look at the results. All right, I think they're just all printed out here anyway because I just ran this notebook. But you can see this confidence interval definitely includes 0, okay? You can see the t-value is very low and the p-value is very high. So what this means is that we cannot reject the null. We cannot claim that there's a difference between these two groups, okay? We have no evidence for that, okay? And if I do the same thing with UN bootstrap t-test, which is a function that's in the hypothesis library, let me run that. Okay, and then there's some parameters here like a trimmed mean and some bootstrapping samples here. And if you're interested, by the way, we can talk about all of these parameters, and it's really interesting. But in this case, you can see that the confidence interval looks very different. It does not include 0. The test statistic is very high, and the p-value is very low. It's actually 0. So in this case, using a robust method against the same data, we can actually reject the null. We can actually claim that there's a statistical difference here. And in this case, with this test, we would interpret the data as males want more sexual partners in the next 30 years compared to females. Now, I want to be very careful here. I'm not saying that robust statistics will always give you a significant result. Sometimes they both come out non-significant. Sometimes it's the opposite result, that the bootstrap test or a robust test of some kind will come out non-significant, and the traditional test will come out significant. And there's a good reason for that, because traditional tests, under some circumstances, lead to incredible inflation of type 1 error. And I'm going to show you a bit about that soon. So I want to be very careful about what I'm saying here. I'm also not saying that robust methods solve all problems we might encounter in the real world. But we want to try to, this is my logic anyway, this is the logic that I think makes sense. We want to try to find methods that work well under normality, just in case, but continue to perform well when distributions are not normal, right? That makes sense, right? We want to use methods that are protective across a wide range of scenarios. And the whole subfield of robust statistics is all about that. And so there are lots of methods to choose from to help you. Okay. All right, one demo done successfully. Let's move on to the next one. It's all fine and well to have this library for robust hypothesis testing. But what I have found over the years is that a lot of the patterns of effects, a lot of the counterintuitive things that you discover are just not apparent, to people who are new to these concepts like bootstrapping and trimmed means and standard error and how does it all work together. And, so when you're talking to reviewers, for example, they may not know this literature. And so it's helpful to have an interactive tool where you can learn to reason about these patterns, because as I mentioned, they're not always counterintuitive. They're not always intuitive. So this notebook, and I'll share a link to this notebook after, it's basically a way of designing your own populations and seeing how all the statistics and metrics shake out when you start with a particular shape of a population. And it's really cool. So just to go through it very quickly, I won't go through every section. You can, for example, select from some predefined, I'm going to zoom in here, some predefined distribution shapes. Like this is an amazing one, contaminated chi-square. Oh my gosh, you thought contaminated normal curve was bad? You should check out contaminated chi-square. You give it some contamination, you plot it. Let me zoom out. So that's how it looks. And then you can start doing things like, hey, how does the mean perform? Is the mean robust? How robust is it compared to the trimmed mean or the one-step estimator or the median or whatever else you want to build into this software? You can set the sample size, look at the sampling distribution, examine the standard error of all of those things, and then you can start to build up an understanding of the patterns because they don't always come out the way you'd expect. Anyway, I can talk more about that if you want, but pretty cool stuff. Just for convenience, I've lined them all up here into a little heat map so you can see like all the distribution shapes and then all the measures of central tendency and how well they perform in terms of standard error. I realize I did not describe what standard error was, but it is one way of assessing robustness of a measure of central tendency. Long story short, the mean is not robust, especially when distributions are skewed and or contaminated, but something more robust like the trimmed mean actually holds its ground pretty well across a wide range of scenarios. And then I have a distribution. I have a section on the distribution of t, which has its own set of big problems. It's a presentation all on its own, the problems that you can encounter with assuming the t curve. And then, just checking the time. And then in the last section is my favorite section. It's kind of like build your own distribution. So rather than selecting from some predefined shape like I showed earlier, you can actually define the skewness and the heaviness or contamination And then this way, you're kind of building a population just based on those two parameters. And this is pretty cool. And once you do that, you can assess type 1 error, comparing a traditional test to a robust test. So I will give you an example of that. If I leave skewness and heaviness at 0, that's basically a normal distribution, and I run this block, I can basically see that the t-test and the robust analog percentile bootstrap test do pretty well in terms of type 1 error. Probability coverage in both tails is pretty equal, and they're both kind of hanging around the nominal value of 0.05, which is good. Now, if I run this a bunch of times, I'll get slightly different answers because it's a simulation, but you'll see that mostly that's the pattern there. If I increase the skewness a bunch and leave heaviness alone, the t-test shows massive inflation of type 1 error, especially in the left tail. And if you were looking at this distribution here of this blue distribution here, which is a whole bunch of t's plotted, you might be able to get a sense of why that might be the case. And then if you increase heaviness and keep skew at 0, what you find is similar to what I showed you earlier, where the percentile bootstrap test, again, has great probability coverage. It still hangs around the nominal value of 0.05 for type 1 error, but the t-test will be a lot lower. This is like an indication of a lack of power under contamination. So this is similar to what I showed you before. Interestingly enough, if you ramp up both of these values, heaviness and skew, then like all hell breaks loose for the t-test, and it has like massive type 1 error, really brutal probability coverage. But if you look at the percentile bootstrap test, again, very good probability coverage and still hanging around 0.05. Okay, I got 4 minutes left. Let me take you through some conclusions. I'm gonna go back to the old slideshow here. All right. So, the normal curve is probably not God's curve. At least, that's what the data seem to suggest. So it makes sense to choose methods that don't assume that. Even small departures from normality can have a big effect on our downstream statistics. I showed you a pretty striking example of power being affected earlier in the presentation, and then just now I showed you what can happen with the t-test in terms of type 1 error. So, you know, like even visually when you're looking at something, it might visually look like a small difference, but it can have a really big impact. So just be aware of that. The good news is that Python resources like Hypothesize and like these interactive simulations, they're here to help, and they're easy to use and available. Please check out Rand R. Wilcox's papers and books. They're life-changing if you want to learn about the field of robust statistics. Most of the ideas I've presented to you today are actually from Rand's papers and Rand's books. So please take a look. And yeah, if you want access to that simulation notebook, just point your camera at this QR code and you'll be off to the races. Thank you very much. That's everything.